Okay, everybody, we are now diving into what is the main point of this lesson, which is when you have a geometric sequence and you add up the terms, how can we calculate the answer? Of course, we can do it by hand by just adding all of them up, but the question is, how can we do it more easily than that? So, that is to say, in a single step, in a single formula. That's our goal here. Let's look at an example. Consider the geometric sequence given by an is equal to 8 times 5 to the n minus 1. So if you list it out, the sequence looks like this. Is 8, and we multiply by 5, and we get 40, multiply by 5, and we get 200, multiply by 5, and we get 1,000, and so on, 5,000, 25,000, 125,000, and so on. It's getting big, and it's getting big fairly fast. The real part of this is find the sum of the first 6 terms of the sequence. Now, I don't want to hide it from you. This is the answer. So the first 6 terms are 8, 40, 200, 1,000, 5,000, 25,000. And if you add those up by hand or using a calculator or a spreadsheet, you will get 31,248. Okay, but what do we do? How do we come up with this number without actually doing each of these additions separately? And the idea is that we can use, essentially, a cool trick to do it. I'm going to demonstrate that cool trick right now, and then we're going to try to generalize it in order to figure out how to do this in general. So just first to make a note, this geometric series, the first term, a1, is 8, and the common ratio r is 5, and those are both just taken from the formula here. There's your a1, and there's your r to the power n minus 1. Okay, so how are we going to do this? Let us imagine that we do not know this answer, and so our goal is to find 8 plus 40 plus 200 plus 1,000 plus 5,000 plus 25,000. Okay. Can we figure out what that is equal to without doing addition like 5 times in a row? That's our goal. Since this is the answer, we know what the answer is, but let's just bear with me. I'm going to call this answer A. Let's pretend we don't know. And we are trying to find A. Okay. So here's what I'm going to do. Maybe I better move that over. So here's what I'm going to do. We want to find A. What I am going to do is down below A, I am going to multiply A by negative 5. And the reason is I'm going to multiply by 5, since 5 is our ratio. Why come up with this? Look, this is the way the trick works. Maybe at the end of this trick you will see. And negative because, well, you'll see, I want things to cancel out. So what I want is to create a line which is negative 5 times A down here. And to do it, I'm just going to multiply each member of A by 5. By negative 5. So 8 times negative 5 is negative 40. 40 times negative 5, you have to maybe do a little work there and see, or you can look cleverly ahead, it's negative 200. 200 times negative 5 is minus 1,000. 1,000 times negative 5 is minus 5,000. 5,000 times negative 5 is minus 25,000. And 25,000 times negative 5, that one requires a little bit of work, but it turns out the answer is actually negative 125,000. And what I want to do is I want to look at these two sums, the top one and the bottom one, the A and the minus 5A, and I want to add them together. So if we think of this equal sign over here, I'm going to add, remember, I'm trying to find what is A equal to. This is my goal. But what I'm going to do is combine the formula for A with the formula for negative 5A. On the right-hand side, A minus 5A is, well, it's 1A minus 5A is negative 4A. And on the left-hand side, let's see what happens. Instead of adding them sort of up and down, 8 minus 40, I'm just going to notice that the second term here, plus 40, cancels with the first term down here, negative 40. Those guys are going to cancel out. So we have positive 40 minus 40, they cancel. When we add 200 and minus 200, they cancel. Look, these things all cancel. 1,000 and minus 1,000 cancel. 5,000 and minus 5,000 cancel. 25,000 and minus 25,000 cancel. The only things that don't cancel are the first term and then this guy. So this is 8 minus 125,000. First of all, that's like magic, so we didn't actually have to end up adding up all of these numbers and all of these numbers. We've managed to jump. All we have to do is a single subtraction. All right, let's do it. 8 minus 125,000. That one we should be able to do in our heads. It's going to be a negative number, and it's going to be negative 124,992. And you can check that because if you add 8 to this number, then it will get you back up to that negative 125,000. Or if you subtract 8, I guess, since it's negative. Okay, that negative 12,000 for 124,992 is equal to negative 4a. Now, what did we want to find? Remember, our goal was to find this number, which is a. And we can now find a quite easily by just dividing both of the sides of this by negative 4. Let's go ahead and do it. I'll put it in purple so we see that it's a modification. And if we do that, we see on the right-hand side, we just get a. That's the original a that we get back there. And on the left-hand side, well, negative 124,992 divided by negative 4 is 31,248. 31,248. Now, this is that number that we were looking for, the number I called A. And if you look back up above, it was given to us in the beginning. Here, when you add all of those up, it's equal to that. And what's like magic is that I never added these numbers up. I never did that work. I just wrote down this series, and then I noticed that almost everything canceled, and I did just a little bit. I had to do one subtraction and one division, and then I got that answer directly. Okay, that is the idea. Somehow we use this canceling business in order to only have to do these sort of two steps, a subtraction step and a division step. When you have a series like this, we call this a telescoping series. If you put these together, telescoping because each piece fits into the next biggest piece and cancels it exactly. So there's some kind of analogy with those old school telescopes that you started short and you pulled them out longer and longer pieces. I think that's the idea going on there. It's worth just noting the vocabulary word telescoping series. Telescoping series are nice because most of the stuff cancels in the middle. It's great. All right. So now what we want to do is we want to find a general formula, which means this is formula for the finite sum of a geometric series. The setup is that we have a geometric series. What we're going to do is we're going to sort of write down the initial setup, and then we're going to go back through this example and see if we can figure out where this came from. So suppose that we have a geometric series, AN, geometric series. AN is equal to some initial term times r to the n minus 1. And we want to find the sum, add up what we get, of the first, well, in the example above, we added up the first 6 terms. But here, since we're doing this in general, I want to just use a letter instead. I'm going to use the letter K for this. Find the sum of the first K terms of this thing. And here's how we're going to do it. So, first of all, there's a way of expressing the problem. This is not the answer, the formula yet, but this is the problem. We can express it in sigma notation because we're finding the sum. The sum of the first k terms we would write like this. Sigma for sum of I equal 1 to k of a sub I. That's what it looks like. Okay, and we want to find, is this just is saying add up all of the terms a1, a2, a3, a4 up to ak. And our goal is to fill in this blank on the other side. What is the formula for adding those up? And in the example that we have up here, the number k was equal to 6. So that what we would like is to find a formula that just involves the number k and then the two things that were given about our series in the beginning, a1 and r. Let's go ahead and see if we can figure this out. All right. Let me see. Okay. So, looking at our answer, the last thing that we did was we divided by this -4. And what I want to do is see if we can trace back that division step. Where does that -4 come from? That -4, -4a, it originally came from combining a minus 5a. And the -5, we chose that number, we made it negative, and we made it that r. So, just to observe, I'll use a different color here. This -4, it comes from 1 minus r. You can imagine that if we're given r, that's equal to 5. 1 minus r is -4, and it's that -4 is the thing that ends up on the bottom of this fraction here. So the last step of all of this is going to be divide by 1 minus r. So over here, I'll just make a little working space. Last step, divide by 1 minus r. Now, the question then is, where did the top of this fraction come from? Well, the top of this fraction, that -124,992, it came from this term minus this term. If we look back at these terms where they came from, the first term, that 8, that is like our A1. It's the first term of the sequence. So this 8 is like an A1. -125,000, forget about the negative just for a moment. That 125,000, that shows up in the sequence. Remember, the original sequence is given here. And they gave us 1, 2, 3, 4, 5, 6, 7 terms of the sequence. We only ended up wanting to add up 6 of them, so we went up to 25,000. But you'll notice that it's the next term after that. So we wanted 6 terms of the sequence. This is the 7th term of the sequence with a minus in front of it. So this was a 1, this was a 7, and there's a minus in front. Now, if we change the number of terms of the sequence to a different number, then this is going to look different. The way that it will look different, if we change this, for example, if we made this the first 8 terms of the sequence, we would still keep a1 here, that's 8, but we would say minus, let me see, if it was 8 terms that we were adding up, we would look at the next term after a8. We would look at a9. And in general, the idea is that the first one is always a1, and this one is always a sub. How many terms are we adding up? We're adding up, in this case, 6. But in general, the number that we're using for the number of terms is k. So it's a sub k plus 1. Okay, so this number, -124,992, it came from doing the following: a1 minus a k plus 1. So, and then we divided that by the number -4 we dealt with before. So somehow the last 2 steps are going to be to take let's just put a little divider, a1 minus a sub k plus 1, and divide by 1 minus r. So this is a formula for it, which I think is very nice. The only issue I have with this formula is that it's not given in terms of a1 and r. It's given in terms of this, there's this k plus 1 running around here. So let's just go ahead and calculate what is a k plus 1. I'll go and do it, let's see, up here, this a k plus 1, right here, in this case it was negative 125,000. How can we jump to that immediately? Well, we can jump to it, let us see, a k plus 1 is equal to, well, we just substitute into the general formula. It's equal to a1 times r to the power n minus 1. And here, the n that we're using is k plus 1. So it's k plus 1 minus 1. So this is equal to a1 times r to the k plus 1 and minus 1. The ones cancel out, and we just have r to the power k. That's our a k plus 1. And what I'm going to do is I'm going to substitute that down below. We're going to substitute that formula into here. So let's just go ahead and simplify. We've got a very nice looking formula. We're now just going to make it a little prettier. A1 minus, and substituting ak plus 1 was equal to a1 times r to the k. And that's all over 1 minus r. Okay, the last thing that we're going to do is to notice that on the top we have a common factor, that a1 is in common. So we're going to pull that thing out. That's a1 times, and then what's left on the top? 1 minus r to the k. And that whole thing is over 1 minus r. And it's a tradition. Typically, instead of writing that a1 on top of the fraction, we write it in front of the fraction. It's fine there as it is. This is basically the formula. But the way that you'll see it in books and other places is that that sum is equal to a1 times 1 minus r to the k over 1 minus r. And this is the formula for the partial sum, the first k many terms of that geometric series. Let's go ahead and write it down. This is our answer. The sum of the first k terms in a geometric series, which has initial term a1 and common ratio r, is, here's our formula. It is a1 times top of the fraction, 1 minus r to the power k, where k is just how many terms you're adding up. Bottom of the fraction, 1 minus r. There it is, this guy. This is our formula for calculating the sum of a series, and what's beautiful about it is that we can do that calculation of a sum of a series with just a couple operations. Maybe we have to do subtraction or two and a multiplication, raise something to a power, but what we don't have to do is add up all of those k many things. In the case of our example, there were only 6 things to add up. That would not have been so bad, but you can imagine taking a sum from 1 to 1,000,000. That would be 1,000,000 different numbers to add, and here you can get that directly without having to add all of them up, and this is exactly how we do it. Okay, in the next video, we will see how to apply this formula. This is the finite sum of a geometric series.